Welcome to another Gaslec podcast, and thank you very much indeed for listening. It really does mean a lot when I look at the viewing figures, so thank you. So this week's episode is all about heat pumps, and there's a few myths about heat pumps, and there's a few facts, and there's a few figures. So obviously we heard all the government stuff that's going on. So, but first of all, here's my friend Sean to tell you about the podcast. Thank you for listening to another Gaslec podcast, the show to help DIYers, new people into the industry, and those who are wanting to expand their knowledge. Each week we'll pick a topic and go into details, and with special guests and listeners' questions answered, we will look forward to some of the conversations. So let's get back to the show. Right, so heat pumps, what are they all about? So we've heard it all in the news and in the media and stuff about heat pumps. They're the way they get portrayed is almost the silver bullet, the goose that lays the golden egg for the replacement, the idea for the replacement of the gas boilers or oil boilers or LPG boilers or whatever fossil fuel you're burning. I don't think it's the truth. It's not. But one thing we can, so if you take out the political side and the spin and the conspiracies of, is climate change a real thing? Is it global warming? Are we coming out of an ice age? Whatever that is, put that to one side. One thing we can all agree on is that fossil fuels will run out one day. We haven't got an infinite supply. So we will run out of petrol, we will run out of oil, we will run out of these, like the coal and all them bits and bobs of the byproducts. So we need to make some sensible choices really and decisions, as a species, on what we're going to do for propulsion, whether it be land, sea or air, or whether it be to heat up our homes, to keep us human beings alive, and to give us hot water and to give us lights and electricity and bits and pieces. So what are we going to do? So one of the things obviously they've made a massive investment in is these thing called heat pumps. Now, if you're not familiar with a heat pump, it's really like an air conditioning unit, just in reverse, which is very similar to what you got in your fridge at home. So it just takes, if you can imagine, the box goes outside. It's quite a large box. Box goes outside in simple terms. And they're called monoblocks. So all of the refrigerant gas is held inside. So refrigerant gas doesn't come inside your property at all. It's just the water that comes in and out, just as it would, almost like another boiler. It's just another heat source. So if you can imagine, if you add 1 cubic metre of air on any given time and it's got 1 unit of heat in it, if you can compress that down to 10 times its, get 10 cubic metres and put it in a 1 cubic metre box, now you've got 10 units of energy, heat energy, that are inside that box, not one in that cubic, because you compress it down. Very similar analogy. I know you got other frictions and stuff, but like a bicycle pump, a hand pump. When you used to pump the tyres up as a kid, the little bike pump and the little valve that used to come off, the little flexi valve, used to get quite hot. Now you're compressing, obviously, air. There's obviously other bits of friction there, but you're compressing air from its natural sort of atmospheric pressure, and you're pressing it down to force it in up to, whatever it's 20, 30, 40 psi for your bicycle tyres. And then that produces a lot of heat. And that's very similar in a very layman way of saying about how heat pumps work. So that's the sort of the box that goes outside. Now, it's quite a big box. They're not very noisy. They're very quiet. They've got a lot better with their time. And the technology is improving and rolling on. So a bit of a downside to heat pump is something called low temperature heating. So when they start talking about emitters, so an emitter on your heating circuit will be something that gives heat out, like a radiator, like underfloor heating, or skirting board heating, or blow heaters, or whatever you've got. But it's the way that the heat and the water comes into the room for us humans to obviously appreciate. Oh, our pets as well. Big shout out to all our pets. So the big issue that we have is gas boilers, oil boilers, LPG boilers. If I just say the word boiler, then it covers all the fuels. The boilers that are run, they can run at 70, even 80 degree flow temperatures. So they run very, very high. So you can get away with a lot. You can get away with some small pipes. You can get away with some small radiators to heat the space up adequately because the temperature is so high coming into the radiator. and it will heat the room up. The issue we have with heat pumps, certainly with the technology we have at the moment, is the flow temperature is a lot lower. So I'll go into another bit in a minute about that. So if we're looking at flow temperatures around sort of 45 degrees, and we want to get the room temperature like 21 when it's -2 outside, in like living areas, that then becomes a bit of a challenge. So you don't have a lot of temperature differential between a 45 degree flow temperature and the 21 degree air temperature in the room that you want to achieve. The difference between the two isn't a lot. If you've got 70 degrees flowing in to 21 degrees, that's really easy because there's so much heat belting out. But when the heat is so it's quite comparable. It's not, the differential temperature between the surface of the radiator or the emitter and the air temperature, as soon as that gap starts closing up, that ramp of sort of heat transfer sort of slows down. So it starts causing problems there. So then what we have to then do on lower temperature heating, we then have to start looking at increasing the flow rates, so increasing like pump speeds and stuff. Downsides of that, you can get a lot of erosion inside the pipe because the water's got a surface friction, and it can run on and rub and then become noisy. And then worst case, it can start eroding it and you start getting holes in your water pipes. So you don't want it too fast where it's causing erosion and it's causing loads of racket and noise and swishing noises coming through your pipeworks because it's too fast. So the other side is to have bigger radiators to allow that more heat to come into the room, and to have potentially, not always, bigger pipework. We call this like the primaries, as it leaves the boiler and it tees off to each individual radiator. In a standard house, that's usually 22 mil pipework. So in some cases, by calculation, we'd need to change that to 28 just to get the energy at the lower temperature round. But at this point, we need volume rather than velocity or speed to bring it round so we can then get the heat and transfer it all the way through. So Part L, the building regulations, say that when we're changing radiators, even on fossil fuel boilers that we still may be working with, we have to start thinking about, we need to sort of pre-prepare and plan. So that little, we went to a job, we got a job on, I think it's on for next week. The lady was like, oh, we'll have in the dining room, we'll have a 1,000 by 600 double in the dining room area. I said, well, this is a living area. We need to start being mindful of lower temperatures. So I'll get onto that in a second about lower temperatures. But so we need to start future-proofing. So we've gone for a larger radiator to future-proof for when we just start doing lower temperature heating. So on the back of that, lower temperature heating, so whatever boiler we're running at the minute, whatever fuel, doesn't matter. The lower the temperature we can run it at and still maintain a warm home that's heating up in a reasonable amount of time, the better and the more efficient it will be. So if you've got your combi boiler at the moment running, I use the word combi just obviously it's the most common boiler, but if you're running at a 70 degree flow temperature and it's flowing out at 70 degrees, really, really hot, you get a lot of heat loss through the pipe, hits the radiators, they'll start belting out the heat. Fantastic. The little thermostats on there start closing down. Everyone's getting nice and warm and it heats up really, really quickly. Fantastic. If you can reduce that by a couple of degrees and you're still getting a very similar result and you don't notice it, well, bring it down and then bring it down again. And bring it down to a point where it's still working, and it's not that noticeable, and the warm-up times of the property are still reasonable, obviously for the time of year as well. The spring and the autumn, when it's still not too cold outside, you'll notice that you can then just have that a little bit on the lower side, but you'll save energy from that. What's another little thing to talk about? We've got SCOPs at the moment and COPs, which they band around for heat pumps and stuff, but from the fossil fuel point of view, if we can, the lower the fuel flow temperature, the more efficient it will be at this stage for us. So that's a little tip for next season. But going back to the heat pumps, what the show's about actually, this episode, sorry, SCOP and COP. So you hear that, oh, I've got a COP of this and a SCOP of that. So a COP, it basically is just a coefficient of performance. So it's all about 1 unit of electricity in, how many units of heat do we get in? So 1 kilowatt in, how many kilowatts do we get out? Divide it between itself, and then that's our COP. So a COP is almost like a snapshot, right now, what is our COP? What is our coefficient of performance right here on today, this air temperature, this building temperature right now? So the seasonal SCOP, which is what we're really looking towards, is the seasonal coefficient of performance. So it's a 12-month, all 4 seasons all rolled in. So the average in the winter, it won't be as good as it will be coming through into the late spring, when the air temperatures are warmer. So it's the efficiency, and it's just a really basic calculation: how many units of electricity and how many units of energy, heat energy, is it produced. So we're looking around 3 to 4. So that means it's like 3 to 400% efficient. So 1 unit of electricity hopefully will give us 1 kilowatt, will give us 4 kilowatts of heating. So that's the sort of numbers that they're trying to perform. So if the heat pump is oversized, you won't get that SCOP, because it'll go into what's the word? It'll just go into this sort of shutting down continuous phase. And if the heat pump's too small, it'll just be ramping up continuously, running at full pelt, and you won't get your seasonal coefficients. So you'll take snapshots and you'll be sort of maybe breaking even, a SCOP of 1, 1.5. So you can get that wrong. If your pipe work is undersized in the property, or they're not correct, or if your radiators or emitters are too small, then you'll start struggling with your seasonal coefficient of performance figures. So it's a fine balance to get the whole installation designed correctly, with the radiators, with the pipework, to make sure it's all going to work 100%, and bringing it all together for a heat pump. So putting to one side hot water. So if you took out your combi boiler, you've got a hot water cylinder to put in, and where's that going to go? So one of the things that I'm trying to explain, if I can, the lower the flow temperature you can have on your system is something called delta T, which is the temperature difference between the flow and return of the device, so whether it be the heat pump or your boiler. So gas boilers, for any fossil fuel boilers, they're designed to run at about a 20-degree difference between flow and return. So if it goes out at 70, it comes back in at 50, and the pump inside and the burner and the modulator the burner and the fan will all sort of try and maintain that differential temperature of 20 degrees. So the lower you have your flow temperature, that delta T gets narrower and narrower, and that's where you get your efficiencies from. So heat pumps, they're looking a delta T, a differential between the two flows of between 5 and 7 degrees from 20, and that's where you're really getting your efficiency from. Basically, it's all of the heat going out is heated up the room efficiently, and there's hardly any heat that's been lost through the pipework, because it's all been lagged and insulated well, and it's coming through the radiators, the emitters, and then coming back, and between 5 to 7 degrees difference, and that's what it's really trying to do. And the heat pump will modulate its speed down to try and maintain that, because if it ramps up too high, that 5 to 7 will eventually get to 0, which it doesn't want to do, but it doesn't want to get that differential beyond 10, because then the rooms are colder than the flow temperature and the radiators. So it tries to maintain that. So dropping down modulating it down on the speed to maintain that ideal. So that's your delta T, flow temperature difference between the two pipes. So all manufacturers have slightly different heat pump sizes. So we're pairing up with Mitsubishi with their EcoDam range at the moment. So I'm just going through my training with that. I think next month I'm off to their hands-on training at Mitsubishi headquarters, wherever that is. I've got a day with them for fault finding. Fortunately, I'm very good at fault finding, but yeah, so that should be fun. So heat pumps really start about 5 kilowatts, and now this is for your whole house and for your hot water if you've got no other provisions for it. So 5 kilowatts, 6, 8.5, and 11.2 and 14. Now the last two, 11.2 and a 14, from memory, I think they're doubles. So they've got the big fan and the big fan underneath. So they're quite large units and they'll take a lot of electricity as well. So we start looking at, they're all single phase, but we start looking at like a 32 amp supply, which is like a heavy electric shower for your home. That's just to power the heat pump. So we have a lot of electrical considerations to think about. When we are applying, we have to speak to the electrical supplier to make sure that there's enough electricity in your road that can take this extra draw for getting electric vehicles and induction hobs and all these heavy new electrical draws that we have on our system, or on the network. So we have to speak to the network just to make sure that there's enough supply of electricity to supply these beasts as well. So one of the things, like with the different sizes, is that we'd have to do a heat loss calculation of your house. So we'll go around and we'll measure up what have you got on the floors, what have you got on the ceiling, what are the walls made of, how big are your windows, what sort of glass is it made, do you have stud walls internally, do you have brick walls internally, and we put it into an app and it works out each room how much kilowatts we need. So when they work out your heat loss, it's very what it says on the tin really, is how much energy you're going to lose when it's -2 outside and you're trying to maintain 21 degrees in a living area, like in a lounge or dining room. So if you're trying to maintain that at those sort of temperatures, and that's sort of a bit of a, not of a worst case design scenario, but that's like a bit of a typical scenario sort of us in the UK really, certainly in the southeast where we're based. -2 and we're on 21. My wife will want about 23, 24, but that's the design of the system. And you can change the design parameters for 23, 24 degrees at those points. So then what we start looking at is how can we improve, because we could end up going to a point where, well, we need a 14 kilowatt heat pump because your home is so inefficient. It's losing heat through the walls, through the roof, through the cavity, through the windows, through the doors. We're losing too much heat and we need a 14 kilowatt heat pump in a sort of a 3-bedroom terraced house, which is a bit unrealistic, to be honest. Your electricity bills would be so high, then it'll become completely unaffordable. And the cost of the heat pump and putting the government grants aside, it just wouldn't be sustainable as a cost. It'd be cheaper to stay with the gas or with the fossils. So then we start looking at what can we do to bring those figures, make it more efficient and bring those numbers down so you could have a smaller heat pump. So really you're looking around the sort of 5 to 6 kilowatts. That's what you're going to need. So so then it'll be like, do we need to change the windows? Do we need to get the loft insulated? What about the cavity walls? What about external cladding for insulation? If you've got a really old brick building or something like that, you can insulate the inside, you can insulate the outside. Is there a way you can do this to increase your thermal efficiencies within your own home? So a lot of the surveys we do for heat pumps, we're going out and we're looking at the thermal losses of the property, and then we're making recommendations to the customer of, you need to get these things in place first, then we can then size the heat pump to your upgrades. Because if you needed a 14 kilowatt heat pump right now, and then in a couple of years' time you go and put all new double glazing in and it's all super efficient, and now we only need a 6, now your 14 kilowatt heat pump is not working efficiently. It's oversized, it's massive, and it's not going to be getting the best efficiency out of what it's doing. So it's not like put a 50 kilowatt boiler in my house and it's just going to modulate itself down and run and it'll be fine. Heat pumps don't work like that. They've got their optimum sort of performance window that you need to tune the house to almost. So you need to get it into that figures. It's you've got a bit of tolerance either way, but it's not a very wide tolerance. You couldn't go from a 6 to a 14 and expect to get the same figures, because you won't. And of course, the heat pump might be $5,000, 3, 4, 5 grand. I know all the bigger ones, they get quite expensive, and you just start thinking, well, potentially in the future, you have to unbolt that, throw it away, or try and flog it, and then get a smaller heat pump because you're not getting the efficiencies that by design that you want to get, which is your 300 to 400% on your seasonal coefficiencies. So that's sort of the heat pump sizes there. Hopefully it's not too confusing. Another option that most boiler manufacturers are now doing, because almost every boiler manufacturer now got its own heat pump, and Mitsubishi have come out with a range as well that can link in with your existing heating system. So if you've got a combi boiler that's running, and you then put a heat pump in, then there'll be a bit of clever box of tricks to work out when is it most efficient to use the heat pump, and when is it most efficient to use the fossil fuel boiler. So we're getting some more inquiries, and there's a bit more traction in the industry around the hybrid system. So rather than going fully heat pump, which is great for new builds because everything's spec'd up from the design of the place upwards. Certainly in the retrofits in my old 1930s house, for an example. So the hybrid systems is a lot more getting more busy with that, where people are putting their toe in a little bit, even like a hybrid car. So it's not fully electric, but you're ticking that box and you're getting the benefits from the electric side, but you've still got the combustion when you want to drive to Scotland, without having to recharge every 2 minutes. So that sort of industry is getting busier and busier from the hybrid side. So people are doing their little bit and they're investing and doing it. I've done some training with Alpha, and they have their own combination boiler which does the hot water on the fossil fuels, so there's no cylinder required, and then you have a heat pump outside, and off the app you put in your units cost of electricity and the unit cost of gas, and it'll work out whether it needs to more efficient and it knows the inside temperature, the outside temperature, the desired temperature, and then it'll work out on itself off the app. Does it use the heat pump? Does it use the gas boiler? Or does it use a blend of both? For the best efficiencies. So I've not looked into the Worcester and the Valent, but they're all doing the same sort of thing. So there's a lot more buzz around that at the moment. So hopefully at the installer show that I'm going to at the end of this month, end of June, should be able to meet some of the manufacturers and see what new bits of kit are on the market and are coming out as well. Thank you very much for listening, guys. This is Sean from the Gaslec podcast. I'll see you all soon. Thank you. Bye-bye.